Imagine you could build a house that the US government has officially certified as capable of surviving an EF5 tornado, the most violent category of storm that exists on Earth. A house that cuts your energy bills by up to 75%. That slashes your insurance premiums by up to 90%. That requires no replacement roof, no rotting timber, no joints to fail. A house that could, by structural engineering standards, still be standing in 500 years. Now imagine that in a country building over 1 million new homes every single year, fewer than 900 of these homes exist. Not because they don't work, not because they're too expensive, but because the financial system was built for a different shape. This channel is dedicated to uncovering the technologies and engineering solutions that work, but that the mainstream has quietly set aside. If that's the kind of thing that matters to you, subscribing takes 2 seconds and ensures you don't miss what's coming next. Now, let's talk about the monolithic dome. Every year, more than 1 million new homes are constructed across the United States. The vast majority of them are built from the same basic materials they've always been built from: wooden studs, drywall, shingles, and insulation bats stuffed between the framing. It's a system that's fast, it's financeable, and, if the history books are honest, it's remarkably fragile. Every year, tens of thousands of those homes are seriously damaged or destroyed by fires, hurricanes, tornadoes, and floods. Every year, millions of American families pay energy bills they wouldn't need to pay if their walls held heat the way better-designed buildings do. And every year, 900 buildings scattered across 49 states quietly prove that there is another way. These are called monolithic domes. And the story of why so few of them exist isn't a story about bad engineering. It's a story about a system that wasn't designed to accommodate a round building. But to understand why that matters, you first need to understand where the dome comes from and why, across the span of human history, it has always been the most structurally efficient shape we know of. The dome is not a modern idea. It is, in fact, the oldest structural solution humanity ever devised for enclosing space. Around 19,000 years ago, in what is now Ukraine, prehistoric builders constructed shelters from mammoth tusks and animal hides, bending them into curved, rounded forms. They had no mathematics, no engineering principles, no written instructions. But they had an observation. The curved shape shed wind. It distributed weight, and it stood when everything flat around it didn't. 17,000 years before the first concrete was poured, the dome was already the answer. By the 2nd century AD, Roman architects had formalized what those prehistoric builders had discovered intuitively. They understood that an arch, rotated 360 degrees on its central axis, creates a three-dimensional shell that distributes load in all directions simultaneously. There are no weak points, no corners where force concentrates, no seams where pressure accumulates. In 125 AD, they used this knowledge to build the Pantheon in Rome, the largest unreinforced concrete dome ever constructed. That building has now survived nearly 2,000 years of earthquakes, floods, fires, and invasions. It still stands today. The same principle appears in the Inuit igloo, a dome of compressed snow, shaped into what engineers call a catenary curve. That specific geometry converts the weight of the structure itself into compressive force, rather than bending stress. A simple hemisphere under load wants to crack at its base, but a catenary curve doesn't. The shape is its own structural solution. This understanding echoed forward through history, through the domes of Persia, the mosques of Istanbul, the cathedrals of Europe. And it echoed all the way to 1941, when an American architect named Wallace Neff built the first modern bubble house, an inflated structure that reimagined the dome for the 20th century. That Neff's work inspired a generation of builders. Among them, 2 brothers from Idaho who would take the concept further than anyone before them. And, in doing so, change what it meant to build a permanent home. In 1976, David and Barry South had already been experimenting with dome construction for years. They'd explored geodesic designs, the angular, faceted approach popularized by Buckminster Fuller. But geodesic construction kept hitting the same wall. Thousands of joints meant thousands of potential leak points. Thousands of seams meant structural complexity that was expensive to manage and difficult to waterproof. Every joint was a potential failure. So they asked a different question. What if the shell had no joints at all? The process they developed, which they patented in 1977 and 1979, begins with a circular concrete ring beam set into the ground. That ring beam anchors the entire structure. To that beam, a crew bolts what's called the airform, a custom-manufactured membrane of PVC-coated polyester fabric, built precisely to the dimensions of the finished dome. High-capacity blowers inflate it. Workers enter through an airlock. And now you're standing inside a pressurized fabric bubble that will become, when the work is complete, a permanent concrete shell. The first material applied to the interior surface is closed-cell polyurethane foam, sprayed roughly 3 inches thick. This foam is doing 3 things simultaneously. It creates a thermal barrier within our value exceeding R20, one of the highest of any standard building material. It provides the rigidity needed to hold steel and concrete in place before they cure. And it acts as a mounting surface for the rebar hangers that come next. Horizontal hoops, vertical bars, tied across the entire curved surface in 2 directions at once. Then comes the shotcrete. Shotcrete is a concrete mix fired at high velocity through a spray nozzle. Because it's projected rather than poured, it compacts more densely than standard cast concrete. It builds up in layers until the shell reaches 3 to 12 inches thick, the precise depth depending on the size and intended use of the structure. When it cures, what you have is a single, seamless, steel-reinforced concrete shell. From the foundation ring at the ground all the way to the apex at the top. One continuous piece. No joints, no seams, no weak points. Now here's the detail that separates the monolithic dome's thermal performance from every conventional building design, and it's counterintuitive. In a standard house, insulation sits inside the wall cavity between you and the outside. The structural mass, the concrete block, the brick, the framing, sits on the exterior side of that insulation. In a monolithic dome, the insulation is on the outside. The foam wraps the interior surface first. The concrete shell is built on top of it, facing outward. What that means is that hundreds of tons of concrete thermal mass sit on the interior side of the insulation barrier. So when you heat or cool the interior, that concrete absorbs the energy, and it holds it, radiating it back slowly, steadily, over hours. The building becomes a thermal battery. The temperature inside stabilizes. The heating and cooling system has far less work to do. That single design decision is what produces energy savings of 50 to 75% compared to conventional construction. But thermal performance, remarkable as it is, turns out to be the least dramatic thing a monolithic dome can do. The catenary curve of a monolithic dome translates every force, the weight of the shell, the load of snow, wind, seismic shaking, directly down into the foundation as compression. There are no corners for wind to grip. No flat wall sections where pressure can build to a failure point. No roof-to-wall joints that can be peeled apart by uplift. A 300-mile-per-hour wind pushes roughly 400 pounds per square foot against a flat wall. Against the curved surface of a dome, that same wind flows over and around the structure, because there is no face for it to push against. Visual, federal certification documents. FEMA rating graphics. The federal standard for tornado and hurricane-safe rooms rates monolithic domes as providing near-absolute protection from EF5 tornadoes and Category 5 hurricanes. To earn that rating, a structure must withstand a 15-pound 2x4 traveling at 100 miles per hour. Against a standard brick veneer wall, that projectile passes straight through. Against a 3-inch dome shell, it barely scuffs the surface. This isn't theoretical. The disaster record is extensive. In May of 2003, a tornado passed directly over a 40-foot dome home in Polk County, Missouri. A nearly completed conventional house a quarter-mile away was blown into the forest. The damage to the dome, a single piece of window trim. After Hurricane Katrina in 2005, the New Life Family Church in Biloxi, Mississippi, a monolithic dome, was one of the few large buildings left standing in the city. That same storm season, a dome home in Pensacola, Florida, survived 3 separate hurricane strikes in direct succession: Dennis, Ivan, and Katrina. And in 2003, a monolithic dome government building in Iraq absorbed a direct hit from a 5,000-pound bomb. The interior was destroyed. The dome structure itself remained standing. The energy record is equally cleared at in Mesa, Arizona. where temperatures exceed 100 degrees Fahrenheit for 107 days a year. A 3,000 square foot dome home recorded a peak monthly electric bill of $199 during the peak summer cooling season. Comparable conventional homes in the same region averaged $400 to $600 per month, according to utility rate data from Arizona Public Service. In Virginia, one family documented annual total energy costs of $900 for a 2,600 square foot dome home, less than most Americans pay to heat a single-bedroom apartment in a year. At the larger scale, a school district in Wisconsin built 5 monolithic dome structures for a combined cost of $9 million, and the dome design saved the district an estimated $8 million compared to conventional construction before a single utility bill arrived. The numbers are consistent. The structural performance is documented. The technology works. So why does a country building 1 million new homes a year have fewer than 900 of these structures? No one sat in a room and decided to ban the roundhouse. There was no conspiracy, no executive meeting at a lumber company where someone said, "We need to suppress the dome." The system simply wasn't designed for it. And in the United States, that amounts to the same thing. In the U.S., buying a home almost always involves a mortgage. And a standard mortgage approval depends on an appraisal. And a standard appraisal requires the appraiser to find 3 comparable homes that sold nearby within the last 12 months. That system was designed for a housing market made almost entirely of rectangular wooden boxes, because that's what the market has always been made of. Monolithic dome owners, having built something that costs significantly less to run and will likely outlast them, tend not to sell. So finding 3 recent dome sales in any given market is, for most appraisers, functionally impossible. Without comparables, the lender has no value. Without a value, there is no mortgage. Without a mortgage, the pool of buyers shrinks to cash purchasers. Fewer buyers means the resale market is thin, which means fewer people are willing to build them, which means fewer comparables exist. It is a self-reinforcing loop, and the dome is trapped inside it. Many municipalities mandate a minimum roof pitch, a regulation designed to maintain neighborhood visual uniformity. A dome's surface transitions from vertical at the base to flat at the apex. It technically violates a fixed pitch requirement at every single point of its profile. And in states like California, getting a building permit for a thin-shell concrete structure that local inspectors have never encountered can cost more than $40,000 in engineering review fees before a single yard of concrete is poured. The conventional home, meanwhile, has an enormous structural advantage, not in its physics, but in its paperwork. Every inspector has approved one. Every appraiser has valued one. Every mortgage underwriter has processed one. The system is optimized for the rectangular wooden box and has been for generations. The monolithic dome doesn't fail on physics. It fails on forms. So should you build one? The answer depends heavily on where you are, why you're building, and how you're planning to finance it. The shell itself, before interior finishing, runs roughly $75 to $100 per square foot, broadly comparable to a mid-range conventional build. The cost advantage of a monolithic dome is not upfront, it's cumulative. 50 to 75% lower energy bills, dramatically reduced maintenance costs, no wood to rot, no shingles to replace, no frame joints to fail, no pest damage. Insurance premiums that can run 50 to 90% lower than a standard policy if the structure qualifies for an all-masonry rate. Over the lifespan of a building that can last centuries rather than decades, the financial case is substantial. For financing, the path that has actually worked for dome builders involves a specific set of steps. Approach a local community bank or credit union rather than a national lender. Smaller institutions have more discretion. Frame the project as a construction loan rather than a standard mortgage. Work with a licensed general contractor who can present a complete project package that reduces lender uncertainty. It's not impossible, but it requires deliberate navigation. For those who want to understand dome construction at a practical level, the Monolithic Dome Institute in Italy, Texas, the organization founded by the South brothers, runs a 5-day hands-on workshop with tuition between $2,000 and $2,500. Over those 5 days, participants work on an actual dome, applying foam, tying rebar, handling shotcrete. They leave with construction manuals, cost estimation spreadsheets, and blueprints for small starter domes. The workshop also draws working contractors, making it a direct connection to someone who can manage a build for those who aren't taking the owner-builder route. For whom does this make the most sense? For anyone building in a high-risk zone for hurricanes, tornadoes, or wildfires, the case is compelling on safety grounds alone. For anyone in a climate with extreme heating or cooling demands, the energy economics over a 20 or 30-year ownership horizon are difficult to argue against. For anyone building on land they intend to hold for generations, the structural longevity fundamentally reframes the math. For anyone who needs a conventional mortgage approval in a market with no comparable sales, or who is building in a municipality with strict pitch requirements and limited permitting experience, the path is harder and requires more preparation. We started with a question. Why does a building that the U.S. government certifies as nearly indestructible, a building that cuts energy costs by up to 75%, that survived direct hurricane strikes and a 5,000-pound bomb, exist in fewer than 900 homes across the country? The answer isn't that the technology failed. The technology is nearly 2,000 years old, tested in some of the most extreme conditions on Earth, and it has never stopped working. The answer is that the infrastructure of modern housing, the mortgage system, the appraisal framework, the zoning codes, the permitting process, was built around a single dominant form, the rectangular wooden box. And that infrastructure, once established, resists anything that doesn't fit its categories. The dome doesn't fit the appraiser's spreadsheet. It doesn't fit the pitch requirement. It doesn't fit the inspector's manual. So it doesn't get built, not because it shouldn't, but because the system has no sell for it. The Pantheon has been standing for nearly 2 millennia. The Inuit understood the structural efficiency of the catenary curve long before there was a word for it. And a pair of brothers from Idaho proved, starting in 1976, that the ancient principle could be scaled, patented, and built into a permanent family home that outperforms conventional construction on nearly every measurable metric. The physics were never the problem. They still aren't. The question worth sitting with is this. When we decide what gets built, who are we actually letting make that decision? Is it engineers, architects, homeowners, or is it appraisers?